All right. So today, this is a totally new section, but it's not necessarily a new concept because acids and bases, and nucleophiles and electrophiles really have very similar problems, even though they're not the same thing. So let me give you some overview since I didn't send out videos for that, and we'll go from there. What's the date? 9th, 10th. Right, so we're going to start talking about today nucleophiles and electrophiles. This is probably the second most important section in the whole class. Other than the reactions that are coming after this, this is probably the second most important section in the class. Right? There are three major parts. Learning how to do resonance, learning the difference in nucleophiles and electrophiles and how to push arrows, and learning how to predict the products of organic reactions. Like those are the three big things you want to take away. So we're going to talk about nucleophiles and electrophiles in terms of arrow pushing, in terms of bond making, bond breaking, and so on and so forth. So let's talk about, first of all, and we've already kind of seen this already with acids and bases. Bond making and breaking processes, right? And I'm going to start out talking about, this is very important. You have no idea how much I have to reinforce this in part 2, the students taking part 2, who breeze through this part. So we have we'll use a real example. And normally this goes from left to right, but because of the nature of the iPad, don't go further. All right. So if I react these two things together, this nitrogen anion and methyl bromide, right? We could talk about nucleophiles, electrophiles, arrows, all that stuff with one example. So what happens in this case, we know that this is polarized. There's a dipole here. Right, and so the nitrogen is going to attack, since it's negative, it's going to attack what's positive, right? It will not attack bromine. That's very important. So in order to show, I'm going to write the products out first, and then we're going to show how it happened. And we're going to talk about how the bonds got made, how they got broken, so on and so forth. So the product looks like this. Plus X. Right? What do you notice? What changed? From here to here.
The placement of the Br and NH2.
The bromine got replaced by NH2. You're exactly right. This is an example of a substitution reaction. Right, we're going to talk more about that later when we start talking about reaction types. But sometimes when you have an example that's all encompassing, you can catch everything all at once. All right, let's look at how this happens. Right, so the nitrogen, in this case, is going to donate a pair of electrons, carbon. Right. Notice the arrow. It's a double-headed arrow. That's on purpose. In organic, and I think I mentioned this already, When you move electrons, you're either gonna move them in pairs or you're gonna move them one at a time. If you move a pair of electrons anywhere in organic chemistry, you need a double-headed arrow to show it. Now, look at where the arrow started. It started at nitrogen and it ends on carbon. That's another really key piece of information. The nitrogen is what I call my nucleophile. Right, it's my nucleophile. Phile, which is, well, philos, which is one of the Greek words for love. Eros and agape are other two. Phile means lover. Nucleo means nuclei, right? So a nucleophile is a lover of nuclei. What's the charge on the nucleus of any atom? The nucleus, positive. The electrons are negative. They add up to the same number of protons and electrons to make the atom neutral. But the nucleus is positive. So this is a lover of nuclei. Right? And I'm gonna put in parentheses here a plus charge. Every nucleus has a plus charge. That's a nucleophile. Is a lover of nuclei. It's looking for something positive to react with. Over here, the carbon is the most partially positive out of all the atoms. Hydrogen can't make more than one bond, so those are out. Hydrogens are only electrophilic if it's H plus, like in an acid-base reaction. So the carbon, by default, this CH3Br becomes my electrophile. What does that mean? Electro for electron. Phile for love, so it's a lover of electrons. I'll come back to that. Lover of electrons. Does that make sense? Something that's positive is looking for electrons. Something that's negative is wanting to give away electrons. So nucleophiles give away electrons, electrophiles accept electrons. Right? So love of electrons and love of nuclei. So now when I attack carbon with that nitrogen, if I don't do anything, right? If I don't change anything, how many bonds would that carbon have? If I don't change nothing, they'll have 5 bonds. Is that possible? It is not. So in the mechanism, when I show the nucleophile coming in, I also need to show the other group leaving. Right? So then I'm going to break that bond. Let me move down this. Right? I'm going to break that bond. And remember, anytime I break a bond like that, I give the electrons to the most electronegative atom. That never changes. So nucleophile comes in and attacks carbon, and then I'll break the carbon-bromine bond. Bromine, in this case, is what we call, I heard you say it earlier, a leaving group. Leaving groups are specific to a certain type of mechanism, substitution and elimination. Both have leaving groups. The bromine is a leaving group. Let me make this point too. On the electrophile, every site is not equally reactive. So the carbon on the electrophile is what we call the electrophilic site. Right, that's the site where the reaction is going to take place. Not going to take place at hydrogen, not taking place at bromine. It's always at the most positive atom in the electrophile. Carbon is partially positive. It's got a bond to bromine. It's the most logical site. All right. Any questions so far?
Nucleophiles, are they always negatively charged?
It can be neutral.
Okay.
Yeah, I'm gonna talk about that in a second. A nuclear, no, it's good. It's a good question. Let's answer it now. A nucleophile can be negative or neutral. An electrophile can be neutral or positive. Yes. That's a great question. I'm gonna go ahead and write that. I'll write it here. A nucleophile, which you'll see me abbreviate as NU with a pair of electrons. Negative or neutral. Your electrophile, which will see me abbreviated as E plus, neutral, and positive, or one of the key skills in dealing with nucleophiles and electrophiles is learning how to identify what's what. If you can do that, that's half the battle, because the arrows always go the same way from nucleophile to electrophile. All right, so somebody help me out. What bond did I make? What bond did I make in the product? I made a new bond between carbon and nitrogen. Is that right? Right. And in making that bond, nitrogen supplied both electrons. Is that right? I took a lone pair of nitrogen and I used it to attack carbon. So that bond making nitrogen gave both electrons. So this is the type of bond making process is what we call heterogenic. Did we talk about that already? Somewhat. Heterogenic bond making. Got a question, Cameron? Sure. All right. Don't hesitate to interrupt. If you have a question, if you're online and you have a question, ask it. You pay it for it, so don't let anything get past you. So in a heterogenic bond, one atom gives both electrons to make that bond. All right? And then what bond got broken? What do we break? What's that? That's a form bond, and then up here we broke this bond. Is that right? Broke that bond. When we broke that bond, where did the electrons go? Let me fill these in, brother. Where did the electrons go? Right up here, bromine had 3 long pairs around it. Down here it has 4 long pairs around it. So where did the electrons go when I broke the bond? Bromine. I'll highlight. What electrons from the broken bond are here? All right. Questions about that? Any questions? So one atom takes both of the electrons in a bond, right? It's still hetero, but if I broke the bond, it's now heterolytic. Right? Lytic, your biology major, the lice used to cut, break, right? So heterolytic means when I break a bond, one atom is leaving with both electrons. Right, so hetero Down here, heterogenic means one atom yields both electrons to make a bond. So y'all, everybody good? You good online?
I have a question about the.
Go ahead.
So like, it's what I heard, doesn't the lead group has to have some sort of like electronegativity?
It needs to be stabilized. Same thing that's going to stabilize the leaving group, the same thing that stabilizes conjugate bases for acids and bases. Same properties, powers, hybridization, induction, resonance, electronegativity, side. It's the exact same idea. But you're right. A leaving group that's more stable is going to leave faster. Than a leaving group that's less stable. Good question. All right, any questions? So we now know how to identify nucleophiles, how to identify electrophiles, what type of bond breaking and bond making processes happen, whether it be heterolytic or heterogenic. And this is an example of what we call a polar reaction. Polar reaction. Everything has a charge, negative or positive. So that's why we call it polar. Even if it's neutral, it's got a dipole somewhere. So nucleophile, electrophile, right? We have a attack of the nucleophile on the electrophile. We made a new bond, we broke a bond. When we made it, it was heterogenic. When we broke it, it was heterolytic. A lot of times when you're reading, maybe you read some other document other than the book or something like that. Nucleophiles, also called sources. Call it a source. It's a source of electrons. And the electrophile is called a sink. Right? The way I like to talk about this is to think about dishes. If you have a stack of plates and they're the electrons, and you sit them down into the sink to wash them, if the sink is empty, that's the thought process. Nucleophiles are sources and they are electron rich. And then electrophiles are sinks and they are electron poor or deficient. You'll hear both of those terms to describe electrophiles, electron poor or electron deficient. In organic, electrons always have a specific way that they move. They always move from a source to a sink, never the other way around. That's why the arrow started here and ended here, as opposed to started here and ended here. Right? So write that down. If you're watching, write that down, that electrons always move from source to sink. I'm gonna rearrange this so I can feel it. That doesn't change. I don't care what your electrophile is, what your nucleophile is. Electrophile will never give away electrons. Nucleophile will never accept electrons. It's always the opposite. Source to sink. All right, everybody, any questions? Everybody straight so far? Can y'all hear me okay online?
Yes,
Yes,
we
we can.
All right.
Yes.
All right, let me introduce you to the other type of reaction we're going to study, and then we're going to go through the same thing like we did here with the bond making and the bond breaking and arrows and all of this stuff. All right. So if I had, this is actually a reaction we're going to study later. All right, so one type of reaction that we're going to study is a what we call a polar reaction. The type of reaction we're going to look at now is what we call a radical reaction. All right, we're gonna go into detail with both. Right, a radical is simply an atom that has a single unpaired electron. So if you look at bromine, it's got one electron to give away. It's got a single unpaired electron. Right? That's the definition of a radical. Right? This too is going to end up being a substitution reaction. But it won't be a substitution immediately. But this is a type of substitution that we'll see later. All right. So with a radical reaction, this is different. All right. So bromine is actually going to donate that one electron to remove this hydrogen. All right. So we're going to rip that off. How many of you have ever heard of free radicals? Everybody, right? When they tell you drink pomegranate, whatever the pomegranate juice, the commercial, because it's an antioxidant.
Yeah.
It scavenges free radicals. So when you think about what a free radical is, radicals are actually really reactive, and that's not good because they'll react with anything. And in the body, it's even worse because you got more complex biologically active molecules in your body that radicals can affect. So when we talk about these chain reactions later, the reason that the radical mechanism is not always preferred is because it's hard to control. All right. But the way that this happens, let's draw the product, and then we're going to figure out what happens. This is one part of the product plus all right, what happened? What did I do?
You just replaced the lone electron with the H. So
Okay.
therefore the lone electron gets transferred over to the C.
Okay, so I gave, it looks like there's one electron here on carbon. Y'all can't see me point, well, you can see me point at the board, but not the screen. There's one electron on carbon. And then bromine ends up with a bond to hydrogen. Right? Is that what you were saying? But if you notice, bromine only has one electron. So I can't use the same type of arrows I was using in a polar reaction. So I got to change all of that. So the way this happens is I have to use half arrows, what we call fish hooks. Every radical reaction is going to use half arrows because I'm only moving one electron at a time. I'm going to use fish hooks instead of whole arrows. Follow? All right, now I need to take that carbon-hydrogen bond and break it such that I have an electron left on carbon and then one to give the hydrogen so it can make the HBr bond. Go ahead. This is the difference in being in person. I see everything. I take everything as some kind of signal. All right, so I can do this. I'm going to do this. I'm going to take this like that, get one electron back to carbon, and I'm going to take this and I'm going to put it right here. So we're kind of indicating that where these two meet, those two atoms are going to make a bond between themselves. All right. I don't want to write H dot, but I can, right? That's the equivalent of saying that this is this carbon with one electron and the H with one electron. And the reason that's important is because it goes back to a very simple concept. Every bond between two atoms, and it's covalent, has two electrons in it. So anytime I break a bond, I'm thinking, okay, that bond has two electrons. So if I break it like that, with a half arrow going to each atom, one electron goes with one atom, one goes with the other. Are y'all following that?
Yeah.
Right? So what bond did I make? I made this bond down here, didn't I? So this was formed. Right? And each atom brought one electron. All right? So we call a bond that's made like that homogenic, not heterogenic. Hetero means one atom had both electrons and one had none, and boom, they came together. Homogenic means each atom brings one electron to the table. Right? Homogenic. What did I break? So the carbon hydrogen bond, I broke that, right? And each atom took an electron. Is that right? What do you think? What's the term we use for break? Lytic, right? Right. Is this, the bond making is homogenic. What is the bond breaking in this case? Homolytic, right? It's homolytic. So we can put that in. So we broke this. Homolytic. And that means each atom takes one electron. Each atom takes one electron. So when I break a bond homolytically, that's a radical process. In a radical mechanism or radical reaction, there are no nucleophiles and electrophiles. Everything is equal, right? So homolytic, homogenic, heterolytic, heterogenic, depending on the type of mechanism, right? No nucleophiles or electrophiles. All right, this example I use for the radical reaction is actually a precursor to what we call a radical substitution, where we'll eventually put a bromine here, but we're going to cover that reaction in detail. So we're not worried about it right now. Any questions about either one of these processes? Or what a nucleophile is, what an electrophile is, so on and so forth. Any questions? All right, 6 minutes left. All right, so before we start talking about reactions in the sense of synthesis, we need to talk about the types of reactions. So we're gonna do that in the last 6 minutes. And then we're gonna come back and I'm gonna send y'all a bunch of videos to watch, or you can read the chapter, or you can do both. Perfectly. That will make you much more agile when we're going through the discussion. But yeah, let's talk about the types of reactions. And then we're going to come back and talk about the arrow pushing processes and things like that. So let's talk about that. So we'll go through the types of reactions between today and the first part of Wednesday. And then on Friday, we're going to start getting deep in depth with the nucleophile, electrophile. We're going to talk about the energy, K, Q, all this stuff. There's a lot. This section right here is like a haymaker. So you gotta brace yourself because it's coming, right?
I'm already knowing that.
Like we started out like a roller coaster, click, 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 my way at the top. We get ready to, so you gotta brace yourself. All right, let's look at this reaction right here. And remember, if this is skeletal, there are 2 hydrogens on each carbon in this ring. What did I do in this case right here?
You just added the already
There's 1 hydrogen left, and I'm just going to say for the sake of the discussion that there's H plus over here just hanging out. All right. So what I did, in essence, was I swapped out one of the hydrogens for chlorine, didn't I? Is that right? I had 2 hydrogens here. On the other side, I have a chlorine and 1 hydrogen. All right. This is an example of what we call a substitution. for lack of a better, a more erudite definition, substitution means I'm swapping out one atom or a group of atoms or functional group for something else. Swap out one atom or functional group with another atom or functional group. FC is the abbreviation for function. Right. So in this case, I swapped out chlorine for hydrogen. All right. What about here? What changed? On your handout or your paper that you have, write plus H2O on the other side. What's the difference in those two?
The two hydrogens broke off and then the oxygen that was left became a double bond.
Okay, great. So I made a pi bond in the product, didn't I? I started out on the left with 2 sigma bonds to oxygen. And in the product, I have a pi bond. This is an example of what we call an elimination. An elimination is the loss of a leaving group. And we'll explain that when we get to, we're gonna do a whole section on elimination. Resulting in the formation of a pi bond. Anytime you see a pi bond made in the product, that's always the product of elimination. Right, so it's the loss of a leaving group resulting in the formation of a pi bond. Anytime you make a pi bond as your product or in your product, that's elimination. All right, we got 1 minute left. Let's do the one on the top right. What did I do? Right here. There's a hydrogen here. What does it look like I did?
You broke the double bond and made it into,
Double bond. Okay, what else?
you brought the hydrogen up to the oxygen.
So I added, really, in essence, I added 2 hydrogens, didn't I? Because I added a hydrogen to the bottom carbon, and I also added a hydrogen here. Is that right? But there are no hydrogens on this side. Is that right?
Yes.
So this is an example of what we call an addition. Right? Only pi bonds participate in addition. So I took the pi bond, I added some atom or functional group to it and broke it. That's what I'm paraphrasing these definitions. But the idea is that I started out with a pi bond, but in the product it got destroyed because I added something to it. So this is an example of addition. So I added some functional group or atom, pi bond, makes it a bond. Now, this is a nuanced definition because sometimes your pi system might be a triple bond, right? So you might not necessarily go from pi to sigma every time. But anytime you break a pi bond by adding something to it, it's an addition. Does that make sense? Like if I have a triple bond, I'm not gonna go from pi directly to sigma, right? I'm gonna go from a triple bond with 2 pi bonds to a double bond that has 1 pi bond and then 1 sigma bond. So we're gonna talk more about this on Wednesday. Any questions about anything? Everybody good? Everybody kept up? Did everybody online, were you able to keep up?
Yes.
Okay, good. All right, we're gonna stop here. We'll pick up Wednesday. Thank y'all for your attention.
Dr. Russell, can you stay after?
Yes. You wanna start out, just put your message in the chat? Yes, I will post it today. You could just send a private message and then I can respond to that. All right. Stay on top of this. I'm telling you, if you master this section, the rest of the class is gonna be cake. If you sleepwalk through this section, then the rest of the class is gonna be, you're gonna feel like you're in a headlock the whole time. So touch it every day. Few minutes a day, 20 minutes, 10 minutes, 15, every day. Do something. Read a article on the internet about the topic. Read the chat, read a section in the book about the topic. You gotta touch it every day. Yep.
I was gonna ask about, I know you sent me about the two, like a
Yeah.
couple weeks ago.
Did you get in touch with Dr. Murphy?
I have not, I was looking, I was asking, so who should I talk to about that?
Yeah.
So,
I copied him on an email.
oh, okay, okay.
Go find that email and reply back to him. Just hit reply all.
Okay,
And
gotcha.
tell Dr. Murphy,
Would that be
here.
like in the session we reviewed?
It's part 1.
Oh, just part one?
General chemistry.
Okay, oh, general chemistry.
Yeah,
Okay,
GChem.
I got you.
Yeah.
Thank you.
So that's even, it ain't even for this.
Right, I was.
You got that. Get that money, man.
Gotcha.
Yeah. Oh, I'm gonna stop recording. They hear me talking all good.